Okay, so in this way we're going to be looking at MacLaurin's theorem. Okay, so MacLaurin's, should I spell this right? Okay, so we're going to be looking at MacLaurin's theorem. So, first of all, any series of the form A0 plus A1x plus A2 x squared plus A3x cubed continued. Okay, so then you'd have the x power 4 term and the power 5 term. Okay, it's called a power series. Okay, so that shouldn't be anything too new for you. Okay, so they're called power series. Okay, again, your A0s, your A1s, and A2 are just constants. Okay, so for example, it could be 3 plus 4x plus 5x cubed squared, for example. Okay, things like that. Okay, power series. Now, in many cases, the sum of such series are such that as more and more terms are added, the sum approaches more and more closely to a particular limit. Okay. Now, in this case, what we mean by that, i.e., a single function. Okay. So, if you have a power series that does, the more terms you add, begin to look, or if you took the limit, it looks like a limit of another function, okay, then what it says to do, it converges to a limit. Okay. With the keyword being converges, okay? So sometimes a power series can actually converge to a function, and what I mean by a function, it could look like, for example, very similar to like a sine function or an exponential function, okay? A function that you would know is just a single function. A power series, depending on the values, can actually go towards that, it converges, okay? If it doesn't, so if you just add more and more terms and it just keeps going bigger and bigger, then what's the opposite of convergent? What from science? Diverges, okay? It doesn't go to a limit, it goes away, okay? But we're going to look at ones that converges to a limit, okay? So that's where MacLaurin's theorem comes in. So MacLaurin's theorem okay? So under certain circumstances, a function f of x is given by what we can do is we can write this single function as a power series. Okay, and how we do that is the first thing would be our function valued at x equals 0, so f of 0. Then the differential of the function f at 0 as well, divided by 1 factorial x. Then the second derivative of that function at 0 divided by 2 factorial x squared. And the third derivative at 0 divided by 3 factorial x cubed. And so on up until the nth term divided by n factorial x to the power n. Okay, so we can actually change functions such as exponential and sine into a power series by using MacLaurin's theorem here, and that's how we would do it. Okay, so as you can see, we're going to need to differentiate the function plenty of times here and substitute the value 0 to actually get the numbers that we need in front of our x terms, okay, our powers of x. Okay, let's go.
Our formula doesn't have the one over 1.
Over 1 factorial.
Yeah.
So the reason being is 1 factorial, as you know, what is 1 factorial? 1. It's 1. Okay, so that actually does just become 1. So anything over 1 is just the same thing. So that's why you don't technically need that one, because it's just the same as 1. Whereas the other ones do have an impact on it. Okay, but you can see why that would make sense to have a 1 factorial there, wouldn't it? Because it's the x to the power 1 term that's there. Okay. Right, we'll look at an example to show you how this works in practice. Okay. So use MacLaurin's theorem. Use MacLaurin's theorem to expand the function e to the x, okay, as a series of ascending powers. X. Okay, so we know the exponential of x as a function, e to the x as a function. Okay, we want to actually write that as a sort of power series, as a sort of polynomial degree, whatever it becomes that we want to take it up to. Okay, so that's what we can do using MacLaurin's theorem. So if I look at my theorem, I'm going to have to work out a lot of things before I can put it into my power series. So start off with the function f of x equals e to the x. Okay, so this is our solution. Then f of 0, well, that's e to 0. And what does e to the 0 give us? 1. Yeah, f at the power 0 is 1. So f of 0 will be 1. Okay. To differentiate a function, well, if I differentiate e to the x, I get e to the x. Okay, we know that from our formula sheet. Again, put in the value 0, that's e to the 0, which again would give me 1. Okay. Second derivative, well, again, I'm going to get e to the x here. And you can quickly see in this example that it's just going to repeat itself, isn't it? Yeah, because we're not actually changing the function as we differentiate it. So, therefore, I can actually go straight into MacLaurin's theorem and write down what e to the x is. So, e to the x would be, well, using MacLaurin's theorem, it's f of 0, okay? And f of 0 is 1. Then it's f dashed of 0, which again would be known as 1, over 1 factorial. So it's 1 over 1 factorial x. Then second derivative, well, we know that's going to be 1 as well, over 2 factorial x squared. Then it'll be 1 over 3 factorial x cubed plus, and so on. It would go on forever. Okay? And we would just tidy that up by using our factorial. So it's going to be 1 plus 1 over 1 factorial is just 1, so it's x there. 1 over 2 factorial is a half x squared plus 1 over 3 factorial. 3 factorial is 6, so it's a sixth x cubed. And then it'd be the fourth power, then the fifth power, and so on. Okay, so we have actually wrote the exponential function as a power series here using MacLaurin's theorem. Okay, are we okay with that one? Any questions on that? So it wasn't the most exciting example, was it? Because nothing changed with the function. Okay, let's look at a question that actually, when we differentiate, it does change, which means we'll get different values here. Okay, so we'll look at a second example here. So again, I'm going to give you a function to do it with, which is going to be f of x equals the log of 1 plus x. Okay, so again, we know logs are a function, but how are we able to write that as a power series? So we need to use MacLaurin's theorem to get a power series, but we need to get our data first. So f of x, oh, got a glitch here. Oh. Oh no, I'm recording a video too. If this breaks out, I'm going to go off my head here. Okay, we're back in the game. Right. So my function's f of x log of 1 plus x. Okay, so f of 0, substitute 0 into there, I'll get log of 1. And what is log of 1?
0.
0. Yep, log of 0 is 0. So I'm actually going to end up with 0 as my first term, okay, which means that that first term isn't really there, okay, it's 0. Okay, I now need to differentiate this. So if I differentiate f of x, to get f dash x, I'm going to get log, well, we know it's 1 over 1 plus x on my formula sheet. Therefore, to work out the value of that at 0, it's going to be 1 over 1 plus 0, which would give me the value 1. Okay, so f dash of 0 is 1 there. There's a bit more space. Let's go for the second derivative. So I need to differentiate this here. So again, using the chain rule, okay, so you bring 1 plus x up as a power negative 1. What that would yield would be negative 1 over 1 plus x all squared. Okay, so therefore f dash double dash of 0, so I substitute that into there, so it would be negative 1 over 1 plus 0 all squared, which would give me the value of negative 1. Okay. Differentiating this again, so again you'd bring that up to make it a power negative 2, then you'd use the chain rule, so you'd actually end up with the answer 2 over 1 plus x to the power 3, and then substitute the value 0 into that, 1 plus 0 cubed, which would give you the value 2. Okay, and again you can sort of see there's maybe a pattern going to emerge regarding everything we differentiate it and what the value is when you substitute the 0 into it. So the fourth derivative, well, just to show you that one. Okay, bring up to the power as a negative 3. Negative 3 comes down times the 2, so it's negative 6 over 1 plus x to the power 4. Therefore, fourth derivative at 0, that's going to be negative 6 over 1 plus 0 to the power 4, which is negative 6, and so on. Okay, there'll be more and more terms, okay, but we've done enough to see what happens. So, the log function, 1 plus x. So again, if I use my MacLaurin's theorem, so the first term is f of 0. Now f of 0 was 0 for us. Then it is f dash of 0 over 1 factorial, so it's going to be 1 over 1 factorial x. Then it's my second derivative 0, which is now negative 1, so it's negative 1 over 2 factorial x squared. And it becomes plus 2 over 3 factorial x cubed. Then minus 6 over 4 factorial x4. What do you think the next term would be? Do you think it would be positive or negative? Positive, yeah, the next term would be positive, so we know it would be positive, and then my next term would be there, okay? Alright. So, just tidying that up. Okay, so the first term goes away. I'm going to end up with x there, minus a half x squared. Okay, 2 over 3 factorial would be a third. Okay, so it's a third x cubed minus 6 over 4 factorial would be a quarter x power 4 plus so on. Okay, so again here we've managed to use MacLaurin's theorem to change the log function to a power series. Okay, we'll show you just one last example that can be a very useful one, especially when sorting a pattern. So when you see a pattern emerging regarding the differentials and when you substitute zeros into it, you can actually very quickly go up a few levels of the power very quickly. I'll show you just one last example on that, and that'll be it for this video. So example 3, we're going to do the same now, but we'll do it for the sine function. Okay, so sine of x will be our function there. Okay, so the solution f of x. So we know we start sine of x. Put 0 into that. Sine of 0 is 0. Yep, graph starts at 0. Okay. If I differentiate sine, what do we get if we differentiate sine? Cos x, yep. Differentiates to positive cos. And if I put 0 into that, well, cos of 0, where does the graph start? 1. Okay. Second derivative, well, what was it? 0 of x. So if we differentiate cos, then we get back to sine, but it's negative. However, every time we put 0 into sine, we get 0. Okay. Third derivative, we get negative cos. What would I get if I put 0 into negative cos x? Negative 1. Now at this point here, yes, it wouldn't be very difficult to go and get more differentials, wouldn't it? Okay, but you could probably already see a pattern. What do you think the next term here would be? It would be 0. What do you think the next one would be? 1, exactly. And then you can see it's just going to go through the same process. Yeah. So once you spot that, you don't actually need to show that once you've got enough data to prove that. Okay. So again, let's see if we can write sine out as a power series. Oops, playing up again. Let's try this again. Oh, lost my board. So sine of x. We know the first term is 0. Then it was 1 over 1 factorial x. Then it was another 0, so 0 over 2 factorial x squared. Then it was minus 1 over 3 factorial x cubed. Then we know it's going to be plus 0 over 4 factorial x squared 4 plus 1 over 5 factorial x to the power 5. And then so on. And when we spoke about the next term after positive 1, well, we know the next term would actually go back to negative, so it would be take away, it would be the x to the power 7 term that would remain at that point. Okay, so we can tidy that up. So 1 over 1 factorial is just x. Then I'm going to get a third, minus a third, sorry, not a third, sorry, a sixth. It's 3 factorial 6, x cubed. Okay, and then the next term would be 1 over 5 factorial. Can you tell what 1 over 5, what's 5 factorial? Is it 120? Yep. Be 1 over 120 x to the power 5. Then we know the next term would be negative, and it would actually be whatever 1 over 7 factorial x to the 7 would be, and then, okay, you could actually work out that value. So again, MacLaurin series allows us just with our standard function to create a power series. Okay, we've seen that for an exponential, a log, and a sine, a trig function. Okay, any questions about that? Okay, we'll stop the video there.